actually, if we can raise the screens for, well, let's keep it. Let's keep the screens down. I'll share in a couple of minutes. Thanks. All right. Yeah, so where we ended off last time was with this Babar search for E plus E minus to a photon and a dark photon that then decays to dark matter. And that was able to exclude these models of light-dark matter down to epsilons at the level of, sort of 0.3 to 1 times 10 to the minus 3. And one question you might ask is, okay, roughly, and this is roughly sort of insensitive to mass. This is for masses of the dark photon less than about, I think it was 7 GeV was their cutoff. One thing you might ask is, how does this compare to these thermal freeze-out milestones that Philip was talking about yesterday? Which, just to remind you, those were roughly on the level of this variable y, which is a sort of dimensionless combination, epsilon squared times the dark sector coupling times this mass ratio to the fourth. This is the thing that roughly sets the freeze-out cross-section, with the caveat that sigma freeze-out, so sigma freeze-out up to pi's is proportional to epsilon squared alpha dark over ma prime squared minus 2 plus sort of thermal correction, 1 over x freeze out m chi squared. So here I'm just accounting for the fact that the propagator momentum in a dark matter annihilation mode, to say E plus E minus, the propagator momentum, sorry, that should be squared, is roughly twice the dark matter mass plus the extra kinetic energy, thermal energy carried by these dark matter particles. And I'm comparing that to the A prime mass. So if you don't have a fine tuning between the A prime mass and twice plus a little bit the chi mass, then this is approximately going like epsilon squared alpha dark. Oh, and I'm sorry, there's an m chi squared in the numerator. M chi squared over ma prime squared, if there's no fine tuning, and if I wanted to write this in terms of something dimensionless, the natural way to write it is, and then the chi mass is an additional parameter, that would be just y over m chi squared. Yeah?
Just to a numeric question, maybe I could hear you say that, should we think of x freeze out as 20 to 30?
It tends to be a little bit lower for these, like there's a logarithmic dependence, so it tends to be more like in the 10 to 20 range for MEV to GeV dark matter. But yeah, that's the right ballpark. So y is related, apart from this resonance fine-tuning, y is related to the freeze-out cross-section. And what this thermal freeze-out matching to the cross-section you need to get the right relic abundance tells you is that this y should be on the scale of 10 to the minus 13 to 14, depending on whether it's S wave or P wave annihilation, times m chi over an MEV squared. Okay, so clearly comparing this to an epsilon value isn't something you can do directly in full generality, because y depends on epsilon, but it also depends on alpha dark. and it also depends on this mass ratio, whereas this Babar sensitivity just depended on epsilon and to a lesser extent on MA prime. Nonetheless, you really want to know, are these, to what extent are these experiments testing interesting thermal dark matter models? So maybe the first thing to note is that as long as my epsilon is sort of big compared to epsilon squared, so epsilon squared for this case of the bar is 10 to the minus 6 to 7. That leaves me a lot of room here to make this work. So I can certainly construct a model with a large mass ratio or a very small alpha dark where you can get thermal freeze out right at the boundary of what Babar is testing. So certainly it's true that Babar is exploring some thermal freeze out models, right? On the other hand, I can equally make thermal freeze out models with a smaller mass ratio or a bigger alpha dark where Babar isn't sensitive to them at all yet. And so there's more work to do. So people have struggled with how do we make this connection in a sensible and informed way? And 10 years ago, what some of the early papers did on proton beam dumps in particular, and actually a lot of papers on many different methods did this, was they'd pick one M chi that's parametrically smaller than any of the A prime masses their experiments were probing. So say a 1 MeV A prime or something, or half MeV A prime or something. Sorry, half MeV chi. Plug in that M chi. Plug in an alpha dark similar to alpha of the standard model, because that's a reasonable expectation. And you just get a curve from that, which if you fix M chi, much less than all of your MA primes, then you're going to get that epsilon squared goes like this 10 to the minus 13 to 14 times this M chi over MeV squared. Yeah? Oh, the green light is on, but I wonder if it's just, maybe it needs a position adjustment. Okay, I think this might be better. Okay. And then, I mean, what am I doing? I'm just going to carry everything over to the other side. It's not very interesting. Right, and I'd get this big hierarchy enhancement. Yeah?
Turn the light on.
Yes. This is it? Okay. Excellent. Thanks very much. So now if I take a very small M chi, say of order MeV, right, this is going to now go like MA prime over MeV to the 4th power. So I get a rapidly rising epsilon as I go to heavy primes. On the other hand, clearly if I'm considering 100 MeV A prime, say, and I go from thinking about MeV dark matter to thinking about 10 MeV dark matter, I'm getting a very dramatic change in what kind of epsilon I want to be probing in order to test the thermalization of that 10 MeV dark matter. So basically, it is a 4-dimensional parameter space, right? And trying to figure out what slices to show to really tell a representative story was, I think, a frequent source of confusion. Now, so the modern approach to this is to try to reverse the logic. And instead of trying, because Y is pretty well defined, relatively insensitive to parameters, to these alpha dark and mass ratio parameters, there's a well-defined milestone for thermalization try to map the epsilon sensitivity of experiments onto that Y space. And then compare that to these thermal milestones that I've indicated there. The same problems still apply. You still get a very different mapping depending on the A prime mass to chi mass ratio and depending on what choice of alpha dark you use. But there's a sense in which you can try to approach that conservatively and say, okay, how do I project a near worst case scenario of sensitivity onto that plane? And in particular, so basically I'm going to use that definition, plug in an epsilon sensitivity, and then the question is, well, to actually turn that epsilon sensitivity into a Y, what should I assume for alpha dark? Or what should I assume for the mass ratio? Now, this is kind of counterintuitive because I think we all tend to think, well, weak coupling makes things harder. But if you look at this scaling and you think about it that way, how do I map my epsilon sensitivity onto a Y sensitivity? You remember, probing smaller Ys is good. The larger alpha dark is, the larger the Y, in other words, the worse the Y sensitivity for a given epsilon sensitivity. So if alpha dark is 10 to the minus 3, let me just ignore that mass ratio for a minute and imagine it's order 1. If alpha dark was 10 to the minus 3, but bar would be probing, I'm just going to use this 10 to the minus 6 number, but bar would be probing down to Y of 10 to the minus 9. If alpha dark is 1, but bar is only probing down to Y of 10 to the minus 6. So the conservative choice is to consider large alpha dark. Now, how large can we make alpha dark? Well, we know we can't make it bigger than 4 pi. Then the theory totally loses perturbative control. But really, even if alpha dark was like 1, you'd still hit a Landau pole in the tens of GeV scale, depending on the dark matter. So you probably want to think about alpha darks where this theory is perturbative, certainly at least over the energy scales where you're probing it at accelerators, and maybe up to the weak scale or so. Yeah?
So you're saying for smaller alpha dark, I can probe smaller epsilon?
So you probe the same epsilon, but then when you map that onto Y, you probe smaller Ys under the assumption of a small alpha dark than under the assumption of a large alpha dark. Yeah, it's always the same epsilon. So the conservative thing is to map epsilon to Y for the largest alpha dark that you think respects the assumptions of the searches. And roughly speaking, the convention has been that to keep perturbativity, and I mean, it depends a lot on the details of the dark matter model, on like, is it Majorana, whether it's Majorana, scalar, or pseudo-Dirac fermion, that's going to affect the beta function for the dark gauge coupling, whether there's other matter in the dark sector, whether there's really a dark Higgs, or whether you just gave the dark photon a Stuckelberg mass. All of these things really affect the RG evolution. And it's also not clear where you would actually get a problem from non-perturbativity of the dark sector. Like, is it really a problem if it's not perturbative? If it's non-perturbative and you need some UV completion at tens of GeV, considering that this is all stuff that's only epsilon coupled to the standard model, can it go up to a TeV? These are all sort of open questions, but what people have taken as a reasonable heuristic is that you don't want to encounter any Landau poles in this theory down up to about 100 GeV scale. And that roughly corresponds to alpha darks on the order of 0.5. And for some models in dark matter masses, you can get up to 0.7, and for others, you better stop at 0.2. And like, you can really get into the weeds on this if you want to. But it was kind of just a heuristic to begin with. So simpler to just pick a benchmark or alpha dark of the right order of magnitude and understand sensitivity with that. So that's what's usually chosen as alpha dark of 0.5. As a sort of, beyond this, you probably don't want to get much more strongly coupled. Yeah? Good. So dark matter self-interaction bounds can give you alpha dark limits closer to 0.1 as well in the very low mass range. But this also depends on exactly, I mean, different people will tell you orders of magnitude. So this is things like how much dark matter self-interaction is allowed by the observations in the bullet cluster. If dark matter is too strongly interacting, then all of the dark matter would clump together, and you wouldn't actually see two different mass densities in the gravitational lensing in the bullet cluster. The structure of elliptical galaxies. And I think it's a matter of dispute among people who are modeling this and simulating it, exactly what the constraint is on that self-interaction cross-section. People usually say that it requires the self-interaction cross-section over mass at certain velocity scales to be less than something like 1 centimeter squared per gram. But sometimes people will claim that that should be 0.1. And sometimes people will say, actually, it's not really even reliable enough that you can comfortably say 1, but it should definitely be less than 10. So, I mean, this is a sort of complicated astrophysical modeling question. So there is still some uncertainty on exactly and debate over what exactly the right cutoff here should be. But Stefania's right that if you take, for example, 1 centimeter squared per gram and MeV dark matter with a 3 MeV dark photon, you're going to get an alpha dark constraint that's a little tighter than this. I think there's also a prevailing attitude that, yeah, these constraints are probably legitimate, but we want to have a terrestrial probe all the way to alpha dark 0.5 anyway. Okay, so that's alpha dark. Now we want to do the same thing for the mass ratio. Again, we can vary this to pretty much anything we want, except, on one hand, this process for thermal freeze-out is only relevant for A prime masses larger than about 1.5 times the chi mass. Clearly, if the A prime mass was less than the chi mass, it would open up this process kinematically, just even at low velocities. And it turns out up to 1.5, this process can still be important, just with living off the Boltzmann tails. That's this forbidden dark matter model. Did you need to talk to you guys about forbidden dark matter? Okay. And then there's also the not forbidden models that have, I think, a 3 to 2 interaction depleting it. And those both tend to take over roughly around 1.5 times the dark matter mass. So it's relevant for A prime masses bigger than 1.5 times the dark matter mass. It's fine-tuned for MA prime close to 2 times the dark matter mass. So this is a region where this milestone just isn't relevant. It's getting changed. This is a region where the physics of that milestone is still relevant, but the parametrics is really driven by the degree of by the resonance. So you get different scaling expectations. So this model and this Y target really makes sense for MA prime, roughly speaking, significantly greater than. That's what I mean by this funny symbol. Significantly greater than 2m chi. Clearly, the bigger, just like we said, bigger alpha dark led to weaker implied Y sensitivity for a given epsilon sensitive search. If you increase the A prime mass for fixed chi mass, that's also going to make your sensitivity look better. So that makes it easier to access this thermal freeze-out line. So the conservative near worst case is when the A prime mass is relatively close to the chi mass, but we don't want to cross this boundary. So the largest we want to take the ratio, m chi over ma prime, is something like a third. Okay, so this is another common benchmark that's used with the rationale that this is a way to stay in the regime where y is actually the right parameter to describe thermal freeze-out, but at the same time, plot things in a conservative way. So if we want to test this scenario, direct freeze-out dark matter into standard model particles through a light mediator, and we want to test most of the parameter space, we want to make sure that we can reach that y sensitivity for large alpha dark, large m chi over a prime, and these have kind of become the standard benchmarks. So if you take that, then this y sensitivity here, now, under those assumptions, these factors are just constants. That's a half. That's 1 over 81. So roughly speaking, this is it's 1 over 162. You can just round that to 1 over 100 times epsilon squared for standard benchmarks. And so what that tells us is that the bar maps to something like a y of 10 to the minus 8. So it hits this lower line, which corresponded to pseudo-Dirac dark matter. When this exponent is, this squared is 10 to the 6th, or in other words, for m chi greater than about a GeV. So, which is right near the edge of its sensitivity. So for dark matter above a GeV, the bar isn't just probing some of this simple thermal freeze-out dark matter parameter space. It's probing most of the thermal freeze-out dark matter space. And I've spent a little bit of time on what seems like sort of simple and arbitrary numerology, but because this is ubiquitous in the way this sensitivity is talked about in the literature, but hopefully it's clear. We want to go basically every experiment that covers new epsilon sensitivity is also going to cover some models of thermal freeze-out through a light mediator. What we want to do is figure out where do we have to get in order to cover most models that don't involve any fine-tuning. And this is the procedure that's become standard in the literature for defining most, is to take these two benchmarks here. All right. Does this seem to make sense to people? Do you want to talk about it more? OK. I will come back after I've introduced a couple more experiments to actually looking at the parameter, some different slices of the parameter space that sort of show how conservative is this choice really, what space are we leaving out. But I think first, I wanted to talk about a few more production modes. So I'm going to focus on electron beams here. And that's not because electron beams are better for dark matter searches than proton beams. It's because electron beams are better for blackboards than proton beams. I can write down a lot of analytic expressions, whereas the cocktail of processes that's responsible for dark matter production at proton beams is actually very complicated. So maybe I'll spend a couple of minutes on that, just so you guys have some sort of basic familiarity with the proton beam production. I'm going to talk about this as proton-proton production. And you can either think of this as proton-proton collider production at the LHC, but the same reactions are going to be different, are going to be relevant when a proton in a fixed target experiment hits a proton in a nucleus. So one thing that'll happen is that these proton-proton collisions produce a lot of mesons, right? You just have standard QCD interactions, min-bias interactions. They produce pi plus or minus, pi naught, and eta mesons. At the LHC, I think it's order 10 of these on average per min-bias event. That's sort of logarithmically dependent on energy. And so pi naughts can decay to a photon and a dark photon, as long as the dark photon's lighter than 100 MeV. Etas can do the same thing with a higher mass threshold. You also have Proton Bremstrolung. So I'll just radiate off a dark photon off of one of the two protons. This has, in many ways, it's similar to the electron Bremstrolung that I'll talk about later. But an important difference is that the proton isn't point-like. And so you have to take into account the proton form factor and the contributions of these hadronic resonances, the vector resonances, so like the omega and rho and phi resonances, in order to get a good model of this production. And then, so this is where I really think of the constituents as protons that are staying pretty elastic, but just bremming off at A prime. And then you also have Drell-Yan-like processes, of which, so QQ bar going to a photon, going to typically not a photon, but a gluon at leading order, plus an A prime. Or you can, of course, add quark gluon processes as well. And there's challenges to modeling this as well, especially in a low PT region, because it really relies on PDFs at extremely small x and at a very low momentum transfer scale q squared, where QCD is getting strongly coupled and some of the PDF sets stop making a lot of sense. And then on top of that, there can be sources that are relevant, for example, at LHCb, from heavier meson decays. There's a rate of decay of the D star, 0 to D0, usually produced with a photon, and that can produce a dark photon. And this is something that LHCb has proposed to use. So there's a lot going on in proton collisions. I think the 2017 paper on phasor is a really good reference on especially the low PT processes. There's also and so they focus on these. These are sort of the most relevant for phasor. These Drell-Yans, like I said, are hard to calculate at low PT, but Atlas and CMS have done some lepton jet searches where they're looking at higher PT production of a dark photon that leads to some very collimated E plus E minus pairs that are isolated from everything else. And these tend to be the processes relevant for that. And then this is useful for a sort of extra mass constraint on vertexing. At LHCb. So that's just a sort of very cursory overview of proton processes. And again, I'm shortchanging proton beams here. There's a lot of cool things they can do, and I'm not doing that out of disrespect for protons, but just in the interest of being able to write down analytic formulas. I'm going to focus on electron beam depths. Okay, so we talked about E plus E minus colliders. The next major lepton beam class of searches is electron beams on a fixed target. And I'm going to start here by talking about beam dump experiments. And in particular, one that was run in the 80s that set powerful constraints is E137 at SLAC. And this is actually an interesting case for historical reasons as well. Apart from being a 1980s experiment that's still like setting, that's still setting respectable limits on models we've invented in the 21st century. This was also an experiment that was co-proposed by James Bjorken and experimental colleague. James Bjorken, otherwise known for Bjorken X and deep inelastic scattering, deeply influential theorist. And he also is one of the leaders of this experiment. In fact, that was how I got to know him. Not because of his trailblazing theory work, but because I was trying to understand the sensitivity of this experiment to dark photon models. And so he was the natural guy to talk to. Okay, so so the basic setup here for any electron fixed target experiment is that you have some energetic, several GeV typically, or several to tens of GeV electron, and then it's going to hit a target. And sometimes this target is a thin slab of material, sometimes it's a thick slab of material. Sometimes it's very complicated water-cooled beam dump with all kinds of materials in it. But for our purposes, most of the cross-section this electron is going to have is for interacting coherently off of nuclei. And the reason the interaction with nuclei is more important than the interaction with atomic electrons is, to start with, that you can actually extract more momentum from a nucleus, more invariant mass from a nucleus, because it's so kinematic phase space is larger. There's an electric charge of Z, which means that all of these cross like Z squared, compared to scattering cross sections off of electrons. Each one has a charge of order 1, and you only get Z of them. So there's automatically a number enhancement as well for production of nuclei. So this is just an electron scattering off of a nucleus, Coulomb scattering, but you have initial or final state Bremstrolung as well. And instead of producing a photon, you could produce a dark photon. This is the main process that's considered in electron fixed target experiments. It's not the only process, and I hope at the end I can quickly come back to one more that has some interesting sensitivity. But this is the sort of basic one that you start from. And okay, this is earlier I just wrote down a cross section for a 2-to-2 process. It's a little harder for this 2-to-3 process, where generally, if I'm thinking about a heavy nucleus, the beam energy is much less than the prime mass electron. There's a lot of different scales in the problem. In practice, you calculate these things using some cross-section tool like MedGraph, and you can model this in Monte Carlo to good accuracy. Yeah.
So with the signal here, does it look like missing energy?
So I haven't. I'm actually going to talk about 3 different signals. Why don't I introduce one, which is actually going to go back to the visibly decaying dark photon, so it goes back to E plus E minus. And for this kind of decay, these beam dump experiments are in the long-lived regime that I talked about in the first lecture. So the way E137 actually works is there's, I think, a 30 GeV beam, impinging on a fairly thick target. And then this fairly thick beam dump, and then there's a hill behind it. So I think it looks more like that. This is 200 meters, roughly. And then there's another 200-meter flat area behind the hill. And downstream of the line of sight of this beam, there's a detector that's got about a 3-meter cross section by 3-meter cross section. Do you have a question too?
Yeah, it's 2 on the production.
Okay.
So for these energies, could you also think about scattering off the quarks?
So you do have enough energy to see the quarks, but in those cases, so you lose this coherent enhancement. So yes, that exists, but it's going to be subleading by power of 1/1. Well, so the first thing you might ask about is scattering off of individual protons. That's subleading by 1/z. Then if you want to compare an individual scattering off an individual proton to something where you're really deep inelastic scattering off the nucleus going into quarks, then there's, I mean, you could kind of think about the individual quarks having smaller charges, so you're going to have a suppression there as well of like, 2/3 squared or 1/3 squared for the individual quark. The main thing is we're going to focus on this coherent process because it scales like z squared. As you go to higher A prime masses, that becomes a less good approximation, and you have subleading processes that scatter off of individual protons. Yeah.
Sorry.
Oh, okay.
So you mentioned you might want a thin target
Yep.
versus a thick target. Why would I want a thin target?
For different kinds of signals. So I never actually finished answering your question. So maybe I should go back to, so I can actually give an overview before we get into the cross sections of kind of 4 different approaches you might take to looking for 2 approaches to visit conceptually, and then 2 approaches to the dark matter production case, so that you have more of an idea of like what kinds of experiments this process would be relevant to. And then I can get into sort of how to think about the cross section. Does anybody have a question that they want to ask before I explain the experiments, though? Yep.
Yeah, so if the z-squared enhancement here is important, is it ever useful to consider, say, heavy ion collisions where you get the z to the 4th enhancement?
I think the luminosities that you get are suppressed by more than that. So compared to say an electron beam dump, the luminosities are suppressed by more than that z squared that you would win. And then the other thing is just that, well, at least for prompt signals, a heavy ion collision is going to be a very messy place to look for 2 leptons. I don't know if anybody has looked at, for example, maybe one of you knows. Has Phaser looked at like fixed target signals? At signal yields from heavy ion collisions? And is there an enhancement there?
I just want to check the
Okay. Yeah, I think that's a kind of application, right, where you have, because where you're going to get that z to the 4th enhancement is in the sort of glancing collisions that are going to tend to produce low PT stuff that you'll see close to the beamline. And it's way too messy if you're looking for a near decay, but if you're looking at a very distant detector like Phaser, you might still be able to see something. But yeah, as far as I know, that hasn't been considered. And that's true, yeah.
Do we need to worry about screening of nuclear charge?
We will, yeah. But I'm delaying the cross section until a little bit later. Okay, so overview of signals. So this is a schematic of E137. So clearly you have no instrumentation until 4 meters downstream of where these electrons are interacting. And anything that you produce in the first 200 meters that's a standard model particle is going to stop in this hill. So this is not going to be sensitive at all to any kind of promptly decaying dark photon, the kind of short lifetime that we were looking at the bar. What it could be sensitive to is the much longer lifetimes that I was talking about getting for epsilons at the 10 to the minus 6 level, where your dark photon could actually travel through this hill, and then it decays somewhere around here to E plus E. And what they were looking for is basically any signal in time with the beam. So any one of these two electrons going through the detector would have been a signal. So that's use case 1 for E137 for long-lived decays. The second use case is, what if the dark photon's decaying to dark matter? And that's going to be a prompt decay. So you'll produce the dark matter way up here in the beam dump. But it's also a very weakly interacting particle. And so it can actually traverse this whole region, and then you can look for a small chance of that dark matter particle scattering somewhere in this detector, giving you a recoil electron. So dark matter comes in, energetic electron comes out. And that would be a second use case for E137. So dark matter scatters in the detector. I still haven't gotten to the thin target. I will in a minute. Yeah?
It seems like they'd be very limited by the fact that this detector is only 3 meters tall. Is there some reason that they wouldn't make it bigger to see more angles?
So money is one reason. It costs L squared times the cost to build something of dimension L. When we talk about the kinematics of this process, you'll also see that it's not as bad as it looks. And I guess yeah, but certainly building bigger detectors to the extent that you can afford it certainly helps, especially at higher dark photon masses. But this is kind of the realistic scale. So for these dark matter searches in particular, another trend that's been going on, I mentioned proton beam dumps as being a little harder to do on a blackboard, so I'm not going to talk about them as much. But one of the attractive things about proton beam dumps is that you can basically do a proton beam dump experiment at an accelerator-based neutrino experiment. And so, for example, Mini-Boon has done a run where they changed their target configuration a bit to try to reduce the flux of neutrinos that they produce. Ran for a little while with a sort of deliberately mistuned beam. And then they used the whole Mini-Boon detector, which is bigger than 3 meters, for this. And there's talk about doing similar analyses with the ton-scale coherent detectors and with the Dune-Near detector and things like that. So there are efforts, especially at proton beams, to use large detectors that are being built for other purposes to do similar searches. Were there other questions? Yeah? So what I'll get to in a minute is that not in a minute, towards the end of the lecture, of the second lecture probably. So when you calculate the scattering rate, the scattering probabilities that I'll motivate for the detector are at the scale of 10 to the minus 7, 10 to the minus 9. So the hill and this dump area are a lot thicker, a lot more material by 2 orders of magnitude, but the probability of scattering there is only 10 to the minus, it's like still 10 to the minus 5, 10 to the minus 6. So most of the time they go through all the way, and there's no suppression of the signal from scattering in the hill. Now, another thing you might be asking is, what if we just consider scattering, say, near the end of the hill? Would that be a better source of signal than scattering in the detector? And I think for that, so I have not actually estimated it. I think the geometric acceptance might be quite a bit worse for that, but I haven't actually calculated it. Maybe that's interesting. At most, I think it would be an order 1 enhancement of the signal. And the reason for that is that even though the dark matter can travel long distances without interacting or sort of losing its energy, the electrons and positrons can't. They would typically start an electromagnetic shower in here and get contained within like 10 radiation lengths of material, which I have no idea exactly what the radiation length of soil is. It's not a compound I think about frequently. Let's say it's probably a few to 10 centimeters scale. So you're getting maybe an extra meter worth where you could produce an electron and still have some fairly energetic electrons reaching your detector. So it's not as big as you certainly don't benefit from being able to produce the electrons and positrons in this whole material. So somebody asked about thin targets and why you might want to make a thin target. One can think about thin targets, again, for both cases, both for the dark photon decaying to E plus E minus, and for dark photons going to dark matter. And I think I want to save the dark matter case for later, but I can just sketch out what. So I mentioned earlier when I was doing the classification, there's experiments like APEX, MAMI, and then the MESA proposal, and dark light that are all looking for promptly decaying dark photons. So there it's an invariant. It's just like the Babar case that we talked about. You're trying to measure the invariant mass of the electron-positron pairs very precisely, and look for a signal over a bump over a smooth background. And it turns out, by having an electron hit a fairly thin target and using this process, you get both the z-squared enhanced cross-section and a much higher luminosity than Babar would. So for looking for low-mass dark photons, this is a more efficient way of producing them. And of course, enhancing your signal yield is enhancing your sensitivity. And so people do experiments where they try to produce an E plus E minus pair in a thin target and then very precisely measure their momenta and angles so that they can work out the mass of the E plus E minus pair and do a search very similar to the one that was done at Babar. You might ask, why do a thin target rather than a thick target? And it has to do with the same multiple scattering effect that we were talking about at Babar. If the target's too thick, then before they even leave the target, the electron and positron are going to scatter. And you lose the angular information that you need to reconstruct their mass. Yeah?
In this case with the thin target, is there something that distinguished this E plus E minus pair from standard model produced?
No, it's just like Babar, where you have a big standard model background and you're looking for a little bump over it. But you can try to improve on mass resolution significantly in the low mass range. And well, actually in the low mass range, it's like 1 MeV is what they can, at least what APEX can achieve. Dark light, I think, and MESA might do a little bit better. And you can, but the main thing is they get much higher yield. And remember, we had this sort of fixed sigma, well, fixed up to order of a few, factor of signal over background times signal, the square root of which, and this signal is a production cross-section times a luminosity that's controlling your sensitivity in these cases. And the luminosity is way bigger for fixed target because instead of just colliding a bunch of 10 to the 11, a bunch of electrons on a bunch of electrons, you could collide a comparable number of electrons on sort of mole scales of material. So you can get high luminosities, and you have a much enhanced cross-section because of this z-squared enhancement. So that's why the fixed target programs have been done with thin targets to look for E plus E minus in the prompt cases. And then there's also displaced decay searches, which tend to use somewhat lower luminosities, both lower current beams and thinner targets. But then, so HPS is the main one with an electron beam, and it uses a forward silicon tracker to reconstruct displacements of the decay production from the target position. And again, it's lower luminosity than these kinds of experiments, but it can still beat the luminosity of something like Pabor, or at least the cross section times luminosity. So that's an overview of thin targets for the visible cases. I think I want to save the thin targets for dark matter for a little later because that's a longer explanation. So I need to switch boards to go over the production physics. Well, any more questions about the sort of high level of the experiments before I move on to production physics? Okay, so I'll go through and estimate. I wasn't going to talk about these experiments in detail, but I want to estimate the sensitivity in both of these modes for E137. And then I'll talk a little bit about the invisible, the missing energy or missing momentum searches, which can use thin targets for dark matter towards the end. Okay, so this is kind of inconvenient board spacing. Actually, I'm gonna do this up and erase protons so that I can have some continuity over here. And please, I have the feeling I'm writing a little smaller and using the edges of the boards more today than in the past. So just yell at me if you can't understand what I'm writing, and I might just need the wake-up call. Okay, so I want to go back to estimating the rate for these. And like I was saying, usually you'd use a full Monte Carlo to calculate it to actually analyze the sensitivity of an experiment. But there's a common approximation. That's made, and this is described in the case of electron beams by some 1970s papers by Tsai and Kim and Tsai, who worked out a lot of electromagnetic processes these ways, including an ALP production process that's very similar to our dark photon process. I was hoping that I could give a sort of much more intuitive derivation of this approximation than I was actually able to derive in a simple way. So, but I ran into some confusion on that. So I'm going to try to give a heuristic explanation, but it won't be a heuristic explanation that approximates a derivation. You're just going to have to believe a lot of stuff and refer to these papers for the sort of mathematical arguments. The general picture here is that what we really care about is the A prime kinematics. We can average over everything else. In most cases, the nucleus. So we're going to average over non-A prime kinematics. And I can think about this as averaging over the recoiling electron kinematics or as averaging over the nucleus kinematics, which is how I kind of like to think about it. That nucleus, we know, so the mass of the nucleus is much greater than the energy. And a nucleus can only take a certain amount of translational momentum without breaking up. So really, the inverse size of the nucleus is another thing that has a big hierarchy to the nuclear mass, which will dictate the kind of momentum that can be transferred. That means essentially no energy. So it can absorb momentum but not energy, which means that in this diagram here, this momentum transfer Q to the nucleus is purely spatial, right? That's illegible even to me. Sorry. So this is some momentum transfer Q mu, which is 0Q. And then I'll have some initial beam energy E naught, outgoing momentum K, outgoing momentum. So this is P, which I'm going to assume is E naught 0, 0, E naught if I neglect the electron mass. Some recoil momentum P prime, and then the momentum of my dark photon. And if I'm averaging over the nucleus kinematics, then, or integrate, sorry, not averaging, I'm integrating over it. Then what's left once I specify the A prime kinematics, and a given, so for a given A prime and nucleus kinematics, this P prime is fully specified. As I integrate over over all of the nuclei, then my point is for a given Q, integrating over final state nuclei kinematics is equivalent to integrating over this 3-vector Q. And second, and for a given Q, this is just 2-to-2 scattering, right? Or this is the same kinematics as 2-to-2 scattering, with the difference being that this photon here is off shell. It's the same degree of freedom counting. I have two known incoming momenta, and then 2 outgoing momenta. So I could think of this final state kinematics as really being parametrized by one angle or one variant. And I can characterize by the energy of the A prime and its cos theta when I'm integrating over Q. But for a given Q, it's also natural to work with a Mandelstam invariant. One Mandelstam invariant for the KP prime system is free. And actually, people tend to use U, which is P minus K squared. Actually, I tend to use minus that. Yeah, sorry.
Could
you repeat why you only need to worry about the spatial component of the energy momentum transfer?
Good. So it's because the nucleus, if I'm to consider an on-shell nucleus before and after, it's very heavy. So even if it absorbs a large momentum, so momentum q, the delta energy is going to be q squared over 2m nucleus. And if I'm just thinking of the idealized case for this nucleus infinity, that's going to be 0. And so it's the on-shell condition on the nucleus that forces this q to be, in this infinite mass limit, exactly spatial, and in a more realistic limit, mostly spatial. Yeah?
So I've seen this is for E137, and this is a 30 GeV beam. So what is the material for E137?
So I think it's aluminum, and I mean, I was going. So you're right that I'm kind of so. Okay, so this isn't very valid for E137. It's kind of within a few. Momentum transfers of 30. If you had a momentum transfer of like 10 GeV, that would be enough to significantly make the nucleus recoil. But it's also enough to disrupt that nucleus, right? Completely annihilate it. And it's really in the deep inelastic scattering regime. So that's sort of outside of the, so that's where I was saying this is the other thing that makes it reasonable to think about this small mass approximation, is that in practice, even if you have a high energy beam, this coherent enhanced process also has a limit on how much momentum you can throw at the nucleus without significantly disrupting it. So this is a fairly good approximation.
Why does the fact that there's a limit make that a good approximation?
I mean, what I'm saying is that the reaction will be dominated, that the cross section will be dominated by Qs that are parametrically less than like the size of the nucleus, the inverse size of the nucleus, which is on the tens to hundreds of MeV scale. And so even though this energy is large, the momentum transfer is still much smaller. So this is not completely obvious. You might think, oh, well, the natural scale of Q should be the beam energy. That's actually, for these processes, you're actually dominated at Qs that are much smaller, parametrically smaller than the beam energy. If you ask how much Q do you need, so maybe it would have been more useful for me to have my Q go this way so that I can think of it as at least imparting CM energy. If I ask how much Q do I need to have enough CM energy to produce an A prime, what you find is that you need Q squared to be greater than twice the, sorry. You need mod to be greater than the A prime mass squared over twice the beam energy in order to get enough CM energy to produce an A prime. So this is just from working out like P plus Q 4 vectors squared greater than MA prime squared. The leading term here is a mod Q times E beam. Or really it's the Z component of Q. QZ times E beam has to be greater than MA prime squared. And so you don't need a very big Q. Precisely when your beam energy is large, you can have very small Qs and still be above threshold to produce A primes. And so you can still benefit from that coherence enhancement. Okay, so the nucleus is just kind of, it's kind of just sitting there. It's getting a little momentum kick, but it's not carrying away any energy. One way to think about Weizsäcker-Williams is that you're just approximating that nucleus as a source of photons coming from its electric field. So you can think of there being an effective flux of of photons. which is alpha over pi times what's often called chi, where chi is just defined as an integral dt. T here is going to be minus q4 vector squared. Or in my purely spatial, this, by the way, I mean, I'm simplifying to this infinite mass limit and elastic scattering of the nucleus for simplicity in this lecture. The original papers actually do keep track of the energy of the nucleus piece and of even possibility of inelastic processes. So that's all included within this approximation, or can be included in this approximation. I just wanted to go to the simplest regime for the lecture. Or in this approximation, plus q3 vector squared. And so chi is an integral dt from T min to T max. I'll explain these endpoints in a minute. Of T minus T min over T squared times G2 of T, which is the electric form factor of the nucleus. So this is the thing that goes like z squared. Well, really it's the electric form factor of the whole atom. So if I look at T, it goes like z squared until I hit T of order inverse nuclear size squared, and then it starts falling off because I'm losing nuclear coherence. And if I go to even lower T's, it falls off because of atomic screening at sort of Bohr radius to the -2 scales. So this G2 is roughly z squared between the atomic inverse size and the nuclear inverse size, and then it starts falling off. This one's a little more gradual at when you start either having such low momentum that you're probing the whole atom and it starts looking neutral, or having such high momentum that you're probing individual nucleons and you lose coherence, or you even start looking at inelastic processes. So this is where somebody was asking if you had to take into account the form factor of the nucleus. This is where it comes in, is through this G2. Now these kinematic boundaries, T min and T max. T min is at 0th order, it's this. This is the minimum. So T min is basically for a given kinematics of the A prime that you want to study, how much Q do you need at minimum in order to produce an A prime with that kinematics? So what I did here, this is a global T min. But there's actually a more complicated expression for T min that depends a little bit on the kinematics that you can include if you wanted a more complete version of this calculation. And then the T max is basically, it's actually set by several effects. One is you can't possibly have Q larger than the total, than the lab frame momentum of the beam, right? So that sets a sort of absolute bound on T max. But in practice, you don't really need to integrate to this nuclear size cutoff, and you don't trust this approximation that the approximations that I'm about to make when Q is less than, you want to stick to Q less than MA prime for Weizsäcker-Williams to be reasonably valid. Because the next part of the approximation is going to be taking this effective flux of photons, these are virtual photons, and then basically pretend that the virtual photons are real. which means you can simplify this, and this is not as bad of an approximation as it sounds like. It sounds like a terrible approximation. Come on. Is it virtual or is it real? But you can use gauge invariance to show that actually it's not as big of a problem as you might think. To contract, basically take this mu index, right, with my off shell Q, and that the leading effects are going to be close to what you would get by taking a cross section for this matrix element squared is approximately equal to this alpha over pi times the chi integral for a total photon times a cross section for E gamma goes to A prime E continued to off shell momentum Q. So, I mean, this argument and where this formula comes from are the two things that I was hoping I could find a more compelling derivation for. That's not quite as complicated as within psi, which I did not want to go through in the lecture, and a little more insightful. But I mean, this has been done now many times in the literature, and in fact, there are several papers that have looked at the kinematics both for the electron recoil and for the dark photon in the full 2 to 3 calculation compared to Weizsäcker-Williams. And the punchline of all of them is that to get quantitatively accurate predictions, you don't want to use this. You want to use the full matrix element. But they reaffirm all of the qualitative consequences of this picture. And so I think Weizsäcker-Williams is still a really useful tool for kind of describing the qualitative features of the production in a relatively simple way. That said, it's maybe not that insightful to talk about the whys of it when, at least I've always thought that you need a more insightful explanation than I've given here of why these formulas are valid to really appreciate the structure. So I guess the one other ingredient I wanted to say here is that if T min is small compared to this inverse nuclear size, and generally we're always thinking about cases where T max is big compared to both of these sizes, then it's basically going to be dominated by this region. And it's going to look like z squared times a log of some ratio of t's, where T1 is the smaller of T max in this inverse nuclear size. T2 is the bigger of T min in this inverse atomic size, which generally that log will be sort of order 10 for a lot of the parameter space, but then can run into considerable suppressions when T min ends up here, right? If T min is here, you're only integrating near the cutoff of the form factor, then there's some suppression in addition from the log in addition to the z squared. So what you get at the end of the day is the differential cross section with respect to the A prime energy and production angle is this effective photon flux factor alpha chi over pi. Yeah. Oh, sorry. Okay. Let's take a break now, and I will try to write up the rest of this equation before we resume. I think that's good. Sorry, lost track.